All right. So what I'm going to talk about is artificial perception, communication, embodiment, and expressivity in music. What I mean by those things will become clearer during the talk. So I'll just move ahead. And the outline will be, I will first give a little bit of background. Yeah, already gave a nice introduction, but I'll give a little bit more information of where I'm coming from. And then I'm going to talk about artificial intelligence in music and beyond. So if you want one of the themes, I'm going to give a talk mostly about my own research in music, but it is my hope that some of the ideas from this talk would generalize to other fields of artificial intelligence or multimedia or video, because I think they are really key to how we move forward as a discipline. So I'm going to talk about these four kind of aspects of intelligence, if you want: perception, communication, embodiment, and expressivity, and mention a bit about future challenges and opportunities in these areas. So in terms of technical background, my main focus of research over the last, I don't even know, 20, 25 years has been music information retrieval. I was involved from the early days in the field. Back in 2000, I have published papers in almost every Izmir conference and in most MIR topics. And back in 2006, I organized Izmir here in Victoria, and I have given tutorials on music information retrieval in many different conferences and events. So that's kind of my home territory, so to speak. And in terms of music background, I've been playing piano pretty much from when I started, when I was 6 years old, until today. I've been really happy with this lockdown because I work more from home, so I can play more piano and saxophone. I've done music theory, composition, saxophone performance, and more important, I've played a lot of music in different settings. So I have played in rock bands, I have played traditional Greek music, folk music when I was in university. Throughout university and later at graduate school, I played classical music. I've played in jazz ensembles, and I've done more experimental stuff and free improvisation and new music stuff. So I've sort of, not that I am amazing in any of those things, but I've done enough to understand what happens when you get a bunch of people on stage and they play music together and the complexities that are involved. So, one question that one might ask is, why would someone, why would be interested in music, modeling music perception and creation and technology? Why do we want to have artificial intelligence in music? And there's this famous quote by one of our the grandfathers of computer science, famous computer scientist Dijkstra, and he was a bit skeptical and dismissive of artificial intelligence at the time. That was back in the 60s and 70s, where AI kind of got a bit of a beating. And he wrote, "The question of whether a computer can think is no more interesting than the question of whether a submarine can swim." So he does have a point that if your goal is to develop a particular system for a particular task, then there are solutions that are much better than trying to model how a human does it. So the classic example is if you want to move from point A to point B on a paved road, a car is a much better way of doing it than walking, or a much faster way. So if you care about speed, a car is the right engineering tool. But if you want to build something that is able to climb mountains and swim and jump and go up steps and, you know, fix car tires and all the stuff that a human can do, then that is a much more challenging question. It's interesting whether it's a useful question, but anyway, I just wanted to start with this quote because it can get us thinking a little bit about this process. So my point is that it is actually interesting to see if a machine can swim. So here I have a little video that I'm going to show. So this is a robotic fish. It's developed at MIT. And it's not as fast as a submarine. It can't carry a lot of weight, but it's really interesting because it moves like a fish. And it is in some ways more complicated than a submarine in certain aspects, maybe not a modern submarine, but a simple submarine. So my main motivation behind my research is not always, I've done a lot of very applied and practical research and do a lot of work with companies on building actual systems. But in my academic research, my main motivation is by building these systems, we better understand and appreciate the complexity and beauty of human music making. So it's more like we're trying to do this to understand how it's done rather than, you know, trying to replace human musicians or trying to build a commercial system. So let's move to the next slide. So let's talk about artificial intelligence in music. And there's a famous quote that I love. I always start my data mining course or my artificial intelligence course or whatever I'm teaching with this quote. So the quote is by Mr. Box, who was a statistician, and it says, all models are wrong, some are useful. So I will paraphrase that quote a little bit, and I will say that all artificial intelligence systems are not intelligent, some are useful. So I really do not think we are anywhere near intelligence, and I will make some points about that later. Another thing I wanted to mention is that it's good to have, and I know that a lot of you are graduate students or postdocs, and it's a bit hard to, you're so immersed into what you're doing that it's hard to kind of see a more long-term view of the field, but it's useful to have a driving vision. So I would say that when I was a graduate student, our driving vision was what we would call the great celestial jukebox in the sky. And the idea was that one day in the future, all of recorded music would be available digitally, and there would be algorithms that would analyze it and that would recommend music, that would make automatically playlists, that would figure out which artists you like, which artists you don't like. They would figure out whether you are at the gym or studying and play music according to your mood and so forth. And it's amazing, but this vision is now true. Like when I was describing it 20 years ago, it sounded like a science fiction dream. And today, anyone who uses Spotify or Apple Music or whatever is your favorite way of listening to music, I can access any piece of music that I've ever heard, anything recorded. I've been able to find obscure recordings of jazz that I had listened on the radio when I was young and couldn't find, and so forth. So this all-driving vision to a large extent has been achieved. Of course, there's still a lot of work to be done, but I would say it's now a reality. So the new driving vision, and I want you to kind of keep that in mind throughout the talk, and even though it's not an exact match, but the new driving vision, for me at least, is the idea of a virtual musician. So I want to build a computational system. It can be a computer, it can be a robot, it can be a combination of the two, it can be a mixed reality environment, but it will be something that plays music with humans and feels like playing with a musician. And the other thing is that I hope, and I don't know, I assume that with so many participants today, a lot of you are not necessarily familiar with audio and music information retrieval, but one of the things that we are finding out, and I think that's true in all areas of computer science, is that more and more it's important to integrate a lot of different disciplines in computer science. And you can't just stay in your little corner of the world and say, I'm just doing human-computer interaction, or I'm just doing compilers, or I'm just doing machine learning. But you got to expand and learn the vocabulary of the other disciplines and work with people in these disciplines to develop systems. So if you think of a, kind of the, I guess, canonical example of an artificial intelligence system would be a self-driving car. There's so many disciplines involved. There is software verification, there's software engineering, there's human-computer interaction in the design of the controls, there's machine learning, there's computer vision, there's signal processing, and the list goes on and on and on. I could, drill it down. You find that it's pretty much any course that you have taken in computer science, there is some aspect of that course that is used when you develop a self-driving car. So the other thing I want to kind of mention here is this is not going to be a talk about deep learning. I think that, and that's not because I am a deep learning skeptic, or here I've listed a couple of projects that I've done related to deep learning. So I've had a PhD student working on binary convolutional neural networks and using bit operations. So the very implementation-oriented project. I've worked on UNets for music transcription, so looking at different architectures for the task of automatic music transcription, Siamese networks for singer clustering, and all sorts of other projects. So by now, I think that it's been something like 10, 12 years since deep learning arrived and became kind of a main feature of a lot of our research. I think I have a pretty good handle of what it can do and what it cannot do. So one of the original claims, if you read, deep learning papers, and it's still repeated again and again, like anytime you read a paper, there's a section in the introduction or the related work that has some sentences to the effect that with a deep learning system, you don't need to do handcrafting of features or feature engineering. You just provide the training data and boom, suddenly you get excellent results, better than state-of-the-art handcrafted features. The reality is a little bit more complex. I'm not, again, like I said, I don't want to talk about deep learning, but I just want to mention this, is that in the old days when we were doing more traditional machine learning, you were spending some time searching parameters and searching among different classifiers, and that search was done without, we couldn't really say which one would work better until we actually tried it and measured the performance. So it's well known that you couldn't just look at the data set and said, this will work better with this classifier. But the feature design was a bit informed. So you could say, well, I know something about this problem. I know, for example, how the human hearing works or have some approximation, so I can design features that approximate that. And that was informed. When you work on a deep learning system, there's a lot of experimentation that happens with architecture, layers, parameter search, and that's done blindly or in some kind of automated fashion, but it's not an intelligent search. And then a lot of the difficulty and the domain-specific details end up in the loss function. And what you can see kind of in the evolution of deep learning is that as it tackles more difficult problems, the loss functions become more clever and more engineered. And there have been some advances in architecture like transformers and UNets, but there's still quite a bit of theoretical issues, and it seems to have saturated, and there's a bunch of problems. So I'm going to keep sort of stash the deep learning problem, but I will bring it back. And what I really would like to kind of convey in this talk is that we need to go beyond these black box learning view where we just have a black box system that does a classification or regression task and expect that that will solve all our problems. What did happen is that it was thought that that approach could not solve certain problems. Like people thought you cannot use that approach to do X, where X was playing chess or playing Go or driving a car. And a lot of these systems did much better than we thought they could do. But I still think there's some fundamental problems, and it's exactly these fundamental problems and challenges that I want to bring attention to in this presentation. So the projects I'm going to talk about in this talk are from my own body of work. And when I say my own, like most professors, it's the work of my students and collaborators. And I just had a coordinating role to play. But they go beyond your typical machine learning system and show you what else is needed to make interesting systems. So I'm going to be talking about perception. And for perception, I'm going to talk about a project on teaching a virtual violinist to bow. So I'll explain what that means. Then I will switch gears a little bit and talk about communication. And this is a very important thing because at the end of the day, we as human beings need to communicate with machines. And that communication happens at different levels. It happens at the programmer level or the engineer level, but still we are communicating with a machine, whether it's with a programming language or whether it's with math equations or whatever. And there is also communication that happens with the user, with the driver of the self-driving car. So communication is important, and I will talk a little bit about that. Then the other thing that is important is embodiment. And there is a terrible disease called lockdown syndrome, where your nervous system and your muscles get damaged and you cannot move anything. So you cannot move any part of your body. Maybe sometimes they're able to blink their eye, but you can perceive everything. You can hear everything. You can understand what's going on. You can watch TV, but you cannot communicate back. And that's because your body has been deactivated. And we need our bodies. Our bodies are how we move. Our bodies are how we interact with the world. And I strongly believe that you cannot have intelligence without a body. So I'll talk a little bit of that, some of my work in music robotics, and expressivity, which is, it's the details. It's what makes a singer makes you cry rather than just listening to a singer. It's what makes a poem and not just a random collection of words. It's what makes an actor's performance in a movie make you cry. So expressivity in music is very important. And in our communications, we frequently forget about it. So I'll talk a little bit about that through some projects. Okay, so I'm now ready to start about the first project, but I just want to take a quick break from, let me stop screen sharing and see if there's any questions or comments. I don't see anything in the chat window. Feel free to speak up or raise your hand if you know how to do that in the participant window.
Everybody is learning how to use Zoom nowadays.
Yeah, exactly.
Yeah. So I have comments. In fact, I resonate very much about what you said. Oh, we do have a question here.
Yeah, the question is, what if human can cheat machine? Yeah, that is a very good question. And it's actually, I mean, you can answer it many ways. But the scary part that I think is interesting is, and people are talking about it, but you know, it's one of those things that everybody becomes uncomfortable when you start thinking about it. Because, for example, again, I will return to this example of self-driving cars. We know that self-driving cars have to be safe and have to avoid killing people, right? So a lot of effort has gone to that. Now, what if somebody wants to intentionally use a self-driving car to kill people? What if they're hackers? What if they are, you know, criminals and want to use it? How will we ensure that that doesn't happen? And a lot of machine learning systems in an adversarial setting where an adversary is intentionally trying to fool the machine learning system are actually quite fragile. So it's well known that sometimes deep learning systems, you can change a few things in your input and they can go in a very different direction. So it is an interesting problem. The nice thing I would say, I mean, you know, my interest is in music. There's not much interest in cheating in music. You're just, you know, playing with a computer, having some good time, and, you know, maybe it's interesting, maybe it's boring, but it's not, the stakes are not that high. There's another question, what type of music the machine can generate? Can they generate a symphony? Yes, I would say yes, although that's not necessarily a task of intelligence. Will it be a great symphony? It's hard to tell. Will it be a symphony that sounds very similar to other symphonies? That's probably true. Will it be a symphony that sounds completely different? That's probably not going to be the case. So for example, to make this concrete, if this will make more sense to those of you familiar with kind of Western classical music, but if you hear a symphony by Mozart, it sounds very different than a symphony by Beethoven. If you could have a machine learning system train on listening to Mozart and make symphonies that sound like Beethoven, that would be a huge achievement. What we have today is systems that will take a lot of Mozart music and then generating music that sounds kind of like Mozart. So it's a bit different. It's more imitating rather than being creative. So that's a short answer. I could probably talk forever on this question. So thank you for the questions. Are there any more? All right, so I will go back to the slides and we will move on to, oops, I now have, there we go. Okay. All right, so let's talk about perception. And so perception is how we perceive the environment. It's the input to an artificial intelligence system. It can be vision, it can be sound, it can be whatever, stock market prices. But in our case, we will focus obviously on sound. So when you generate sounds with a computer, so you all have seen people, you can get a keyboard and you can play it and you can hear violin sounds coming out of the keyboard. But so if you sample a sound, like you can sample a violin player playing a single note and you can record it, and then when I press a key, I can hear that note. That sounds very good. But if I want to change the sound, if I want to make it go louder and softer and make a phrase and change the dynamics, when you do that with digital sampling, it doesn't sound very good and it doesn't give you that very detailed control. So there's a technique called physical modeling synthesis that rather than storing the sound kind of in its the sound itself, what it does, it simulates the physics of sound production. So it actually runs a simulation, a physical simulation of how the string vibrates, how the bow works, how the wood resonates, and produces sound that way, rather than storing waveforms. And physical modeling synthesis, it can be very expressive. It can be easy to, it can, not easy, it can be controlled because you are controlling the parameters the same way that a musician does. Like if I'm playing violin, if I move my bow faster, that changes the sound. If I press harder, that changes the sound. So how do we do that? And the thing with control is that it's difficult. So I believe some of you might have either learned a string instrument as children or have friends who have or relatives, but you know it takes a really long time to be able to play a stringed instrument. It's actually remarkable that people play music on violins because it's hard. Like you spend years, my son, you know, I feel like for 4 or 5 years, all he played was Twinkle, Twinkle, Little Star, and it sounded horrible. And then suddenly, in a year, he started sounding good. But it takes time, and it's a hard problem. So, so let's see what's happening. So when you play the violin, it requires constant feedback. So for example, to play in tune, it's not enough to just move your hand to the right position because the same position will sound slightly different in frequency depending on how warm the room is, how much the humidity is there, even the sort of texture of your hand. So a real violin players don't play by exactly placing their finger. What they do is they hear the sound and adjust. They hear and adjust, and that hearing and adjusting happens continuously. And you can do an experiment. You can put some noise canceling headphones or maybe put some noise on the headphones so that a violin player cannot hear what they are playing. They just play, but they can't hear what they are playing. They will sound horrible. Like within a few seconds, you can't hear, they don't sound good. Which is different with a piano player. If you ask a piano player to play something simple, even if they can't hear themselves, usually they can play it sort of okay. So what we wanted to do is we knew that we have this physical model that has a lot of controls, how fast you move the violin, how hard you press it, what finger you're using. And we didn't want to program all that stuff explicitly, but we wanted to sort of teach the violin the same way you would teach a real violin player. You would say, oh, you're not putting enough force. That's why you're not sounding the note. Put a little bit more force, or move your bow a little bit more, or don't hold it too short. Like there's all these instructions, but violin teachers, that's how they do it. They will tell you, do this, do that, show you how to do it, but they are not telling you move your finger 10 centimeters down the fingerboard. So what we basically tried to do is develop a virtual ear. So we wanted to create the sound on the computer, listen to the sound somehow, and decide whether it's good sound or bad sound, and teach the computer how to do that. So this is work by Graham Percival, which is a former student. He did his master's at UVic, and then he did his PhD at the University of Glasgow, and then was followed by postdocs at UVic and a postdoc at the National University of Singapore with Dr. Wang. So he is kind of a connection between us. So I like to paraphrase quotes. So here's another paraphrase quote: with great control comes great fragility. So if you have a system that's very sensitive to how you control it, it also can result in behaviors that are dangerous. So for example, piloting an airplane is much more dangerous than driving a car, because the controls are more complex and you have more control, and you have to make sure that you don't stall or you don't get the controls to a state that will create a problem. And piloting a helicopter is even harder. And you would think, okay, well, can't they just make an airplane so that the pilot never is able to get to a state that will result in the plane falling off the sky? And the answer is that if they could have done that, they would have done that. And they are very close, but still accidents happen. And that's because it's a complex system that requires precise control. So a classic guideline for talks is to always have some equation to show that you do some kind of serious math. So this is my equation slide. So this is the physical model that we use. It sort of solves a partial differential equation. No need for details. The input parameters are what violin string you're playing, what finger position your left hand finger has on the fingerboard, the distance to the bow, the velocity, and the force. So at every time instance, you need to provide numbers for those 5 variables, and those determine the sound that will come out of that physical model. So if you change the finger position, the note you are playing will change. If you change the force or the velocity, both the volume and the sound will be affected in a continuous way. So we have to keep kind of doing that. So the way the system works is that we have a score. The score tells us, for example, what fingers to use and where to play. But then the physical parameters, those numbers that I mentioned, need to be adjusted. So what happens is the physical parameters go to the physical model, and the physical model generates sound. And typically, like in most existing systems, that's where things would stop. Our main idea was to take that sound that's generated by the physical model and feed it back to a classifier, and basically be able to tell if the sound is good or if the sound is bad. And then teach the system to recognize bad sound, either soft sounds or too loud sounds. And then depending on that, go and adjust the parameters, readjust, and keep doing that loop until the sound is good. So it's a machine learning approach, but the point is that it's used in a feedback system that includes, and it takes the role of perception. So I will play you the system without any like virtual ear. So this is just playing the violin with kind of default parameters. So you can hear it has that kind of screechy quality that beginner violin players have. I hope you could hear the sound. Is that true?
Yes, I can hear.
Yeah, perfect. Okay. And so what happens is that then a human teacher just says that note was good, that note was bad, that wasn't too loud, and you keep doing that training. And this is what happens after several rounds of training the virtual violinist. So it's playing the same scale, but now you will hear it sounds much more smooth. So, so you might say, well, that doesn't sound that great. I've heard like people on GarageBand put a bunch of string sounds and it sounds amazing. But in this case, it's a real physical model of a violin simulated, and it does things that real violins do, and it is expressive. So here's a more complicated example. To the left, you can see the score. If you can read music, you will be able to follow along. And to the right, you see a 3D model of the violin. And you can see that the bow and the fingers move in a way that responds to the score. And the sound is generated by literally moving the bow inside the computer in the simulation. So it's not a pre-recorded sound. This is generated by the physical model. Okay, so that concludes my section on perception. And let's take a quick pause and see if there's any questions. So I will stop screen sharing.
All right. We do have a question.
Yes, so can music generation be applied to song generation, i.e. human vocals with instrumental accompaniment? Perhaps. There are systems that generate melodies and accompaniment. And then you could, there's a second part of, do you have lyrics or just singing la la la? And there are some systems that are singing voice synthesis, but typically they're not that great. So you could make something, it wouldn't sound like, an amazing singer, but yeah, so that's, and I should mention here, because this is something that, like, I don't know how to say this. Most people, this is the same thing that has happened with artificial intelligence, is we say, okay, what do we think is a difficult task for intelligence? It's playing chess. Okay, fine. Why? Because there's only a few humans who play very well chess. So we then build a machine and voila, it beats most humans on chess. There's tasks that are much simpler, like, for example, picking out the carrots out of a plate, which a 2-year-old that doesn't like carrots can do. Most 2-year-olds can do it if they don't have any motor problems and vision problems. I think you could take the most advanced robotic engineers and give them millions, and they would not be able to take an arbitrary dish with different types like spaghetti or other types of vegetables and only select the carrots. The carrots could be small or big or soft or hard and do that accurately. So what I'm getting at is I think that music generation is one of those problems like chess. It sounds like impressive, but actually coming up with a score for a piece of music is not that hard. It's a lot of other things that go into the voice or the expressivity, the perception, that are much harder, but we kind of don't notice it. Will music generation be able to take over music engineering editing that is auto-tune? Perhaps. I mean, it's kind of I'm not sure if it will. It's a meaningful question. Like, we still watch people run 100 meters, even though we have cars that are much faster. So perhaps we will always want to watch people, but also we do watch things that are automatic. We listen to things that are to a large extent automatically generated, like a lot of dance music is based on a lot of loops and repetition that are easily automated. So I don't know. I just think it's more interesting to, again, look at the things that are more unique to the process. So this is good because we will get, like, this is exactly the next parts of the talk kind of answer some of these questions. That's a very good question. Does the virtual violinist generally use the same kinds of movement that a human would? I can't play the violin, but from the video, the movement seemed quite natural. Does it ever move in very weird ways, but still sounds good? No, and the reason is it's kind of by construction. So, for example, we don't allow to change the velocity of the bow non-linearly, because you can't, like in real life, you cannot suddenly go from slow speed to fast speed. You have to accelerate to get to that speed. So there's a bit of continuous control. So I would say in general, it mostly results in physically correct movements. But it's certainly something that can happen in other modeling cases, that it would still sound okay, and maybe it would come up to the same sound in a way that would not be what a human would do. Because that's the other thing, is the violin, you can get the same pitch and same loudness with slightly different configurations of the parameters. Like you could have different sets of values that result in the same output. So it's a kind of many-to-one mapping. All right, so I think I will go back to my presentation and screen sharing. So let's see if I can do this right this time. So we're here, presentation. Okay, so let's talk quickly about communication. And I just wanted to mention that we tend to think of communication mostly in terms of human-computer interaction. So, you know, that's pressing buttons, viewing screens, playing games, virtual reality, listening to sounds. But we also communicate with computers in these slightly more idiosyncratic ways. So programming languages are still used a lot to program computers. Those could be either text, or they're programming languages based on connecting visual objects in different ways, but they're still very heavily used when we create software and hardware systems. And we also communicate in a kind of different way than programming when we build machine learning, which is by providing the computer with a collection of annotated data by humans. So both of those are sort of ways we communicate. And one of the things that I would claim is that our communication is very tedious. Like we all, you know, I don't think there's a single human on the planet that would say that it's easier to communicate with Alexa than with another person. And Alexa is a pretty impressive engineering advancement. It does okay, Siri does okay, Google, whatever does okay, but they're nowhere close. Actually, this is really funny. I said Google does okay, and my phone popped up and said, "Hi, how can I help?" So that was entertaining. So anyway, so I'm just going to talk to you about some of the projects that I have done that try to address this communication bottleneck. The first one is a bit more traditional computer science, and the second one involves a little bit of machine learning. So the first one is the ARP programming language, and this is a language that was designed and developed by my PhD student, Jakob Leben, and it has a syntax which is based on recurrence equations. So for those of you who like math and are used to digital signal processing, the code you write is very similar to how you write DSP equations. And it supports infinite and multidimensional and multi-rate arrays or streams. And it does efficient compilation to low-level code using a technique called polyhedral compilation, which I'm not going to talk about in details. But I just wanted to give you a flavor of how it looks. So this is the equation you would write for a filter. And notice that there's nowhere anything about the size of these quantities. It's exactly like a signal processing equation. We say it starts at 0, and the output at position n is basically the input at position n multiplied by b minus the output at position n minus 1. So that's one previous sample times a. And we can generate infinite streams of this filter. This is a infinite impulse response filter. We can work with signals at different rates. We can work with multidimensional streams. So you see here we have basically an image that has two indices, and we can do math with entire signals. So here n is a signal, and we can have this equation where xn is equal to n, and x is a signal, and we just put it into this equation. So so you would say, well, what's the big deal? How is it different than any programming language? In some ways it's not, but this is the thing with programming languages is that things that are a little bit more difficult to express over time become more easy to express, and you work at a higher level, and it enables you to think about things in a way that's easier to communicate what you want. And it's interesting because, you know, we can't, these are languages we have invented. Even the language like of writing equations and the symbols we put down for math, we invented them. People over time came up with these symbols for writing numbers, for writing equations, and they're a way we communicate. So it's important to keep pushing that boundary. So you might think, well, what does programming languages have to do with AI systems? Well, we have to program these AI systems, and it's not just the machine learning part. So that's kind of my quick point. The next point I'm going to talk about is music analysis of audio signals using machine learning. So that's a lot of the work that I have done. Is we focus on a specific aspect. So there's systems that extract the beat from a song. There are systems that extract chords or tempo. And most of them today use data-driven machine learning models. So you train the system with a lot of data. For example, you give it a lot of pieces of music and you say, from this point in time to this point in time, it's a C major chord. From this point in time to this point in time, it's an F minor 7 chord. And then that information is processed by a machine learning system that is able to take as input audio, extract features, apply a classifier, and predict what chord is playing. But that's not how we humans understand music. We combine all that information together, and we don't focus on individual aspects. We sort of usually at the same time combine all aspects. And so that's something that's missing from existing systems. Another thing is that we know a lot of things, and there is no easy way to communicate that to a machine learning system, especially the kind of data-driven ones that we have today. So to give you an example, we know that, so we have a machine learning system that classifies birds. And we find out that, you know, it latches on texture features that depend on the birds having feathers. But there are some birds, like penguins, that don't have feathers. If you are teaching that to a child, you could say, you know, most birds have feathers, but there are some birds, we call them penguins, that swim in the ocean and they don't have feathers. And the child is able to learn that information in that way. There's no easy way to communicate that information to an existing deep learning systems. You could train a system with a lot of pictures of birds that are not penguins, and then another system with a lot of pictures of penguins, and then have a system that's bird that's not a penguin versus penguin. But it's very awkward. We can't just say what we know and communicate that, because these systems only work by analyzing large amounts of data. And the other thing, that there's no easy way to communicate partial knowledge dynamically. So by that I mean, imagine that you have a speech recognition system that is transcribing a language that you don't know. Like, I'm listening to a radio station in I don't know what language, in Russian, and I have a speech recognition system transcribe the Russian. But suppose that I actually am a beginner and I can recognize a few words, and I notice that at some point the speech recognition system selects the wrong word. There's not an easy way for me to say, no, that's not the right word, this is the right word, and have the system incorporate that information. So this kind of incremental dynamic partial knowledge learning is very, very challenging to existing dynamic systems. So, back to the self-driving car example, we would like to be able to say something like, okay, the system has been trained on bicycles. It has never seen a unicycle. I'm driving, I see a unicycle, and it's not slowing down. I would like to say, hey, slow down, there's something moving ahead. And then when it slows down, say, by the way, this is called a unicycle and it has one wheel. From now on, can you stop for unicycles? You can't do that. You could do it with the Knight Rider car in the 80s. I don't know if you know that reference. It was this show in the 80s that had a car that was intelligent. But with a modern self-driving Tesla, you cannot do that. So that is an important shortcoming of existing systems. So a traditional alternative to that was used before data-driven approaches is logic. And in logic, you can have rules like, if you detect a bicycle, stop. But it's hard to handle uncertainty, and it's difficult to integrate data analysis. So I'm not going to go into details, but Markov logic networks is one of the many formalisms. It combines probabilistic graphical models and first logic inference. It's highly flexible, and it can be used for music analysis. So an MLN is a weighted first-order logic, a set of weighted first-order logic formulas that then can generate a probabilistic graphical model. And the logic rules soften from true and false to probabilities. So here is kind of how this would look with some pseudo rules, like a major chord implies a happy mood, and the rule would have a certain weight. So it's not always a major chord implies a happy mood, but it is. And then once you have that, that's how you kind of specify your knowledge base. And then it can generate a probabilistic graphical model that can be used to perform inference. So we have used that to estimate chords. I'm not going to go into the detail, but basically the nice thing is that you can essentially write it down, and what you have is an equivalent model to a hidden Markov model, but it's expressed in a very clean, kind of concise way. But then if you want to include the structure information, so songs have structure like chorus and verse, and you want to say that the chords in the verse are most of the times similar, maybe not exactly the same, but they're most of the time the same, you can express that in this Markov logic formalism. And some of your knowledge can be expressed in the knowledge base, and some of it can be learned from data. So it's kind of does a few of those things that I was talking about being able to combine logic and knowledge with inference and data uncertainty. And we have shown that you can get better results, and you can do different things like estimate both the key and the chords, or if you know the chords, estimate the key. If you know the key, estimate the chords, and so forth. So I'm running out of time, so I'm not going to go into details, but I'm happy to point you to the right place if you're interested. So let's talk a little bit about embodiment. This is it's from the 1200s, and it was a guy named Al-Jaziri, who was an inventor and engineer, and he built this robotic boat. It would just move in the water, and kind of the movement would trigger all these mechanical automatons that would play music. So it was a mechanical system that automatically played music, not electrically, but they were not human musicians, they were machines, basically. I'll talk a little bit about human-machine improvisation. So back in 2004, I joined the University of Victoria as an assistant professor, and Ajay Kapoor was my first PhD student. So he came to me as a new PhD student and said, I want to make a percussion robot that is able to improvise North Indian music with me playing the sitar. And I said, well, you know, that's too ambitious, focus on something more specific. And fortunately, he ignored me. So he actually went ahead and he built that system. So here is this footage of him playing the robot. And actually, if I'm not mistaken, this is in Singapore. Let's see, there we go.
Yes, I can confirm that.
Yeah. So here you have a physical system. It's a mechanical robot that's controlled by a computer. And, you know, on some level, you can say, what's the big deal? I could just trigger samples on my computer and have a similar sound. But the fact that it's an actual physical object makes a big difference. And I think that, you know, we are more and more moving away from everything happening on a screen and a keyboard. Obviously now with COVID, we are back on screens and keyboard, but even things like Pokemon Go show the potential of this blending of the real world, the physical world with the virtual world. So what's happening here is that the sitar that Ajay is playing is a hyper instrument, is an acoustic instrument that has been augmented with sensors to detect what the performer is playing. And there's a network of resistors that detects what fret you're playing. There's a thumb pressure sensor, and there's what at the time we built our own version of the Wii-mote. That was before the Wii-mote came out, for sensing your elbow. So this is how the sitar looked. So it took a lot of kind of more electrical, mechanical engineering work to kind of build this device. But now we had more accurate information about what Ajay was playing in that instrument. And that information was used to drive the robot. So for example, we did real-time multimodal beat tracking, and we're using a Kalman filter. So that's an example, again, of a sort of more DSP algorithm, but it's placed in this context of sensors and actuators, and kind of it's part of a larger system. It's a component of a bigger system that lives in the real world. So here is a newer version of the robot with more solenoids and instruments. And one important thing that we found out over time is this idea of the importance of what is called proprioception. So this is the perception of your own self, of your own body, knowing where your hands are, knowing where your body is. And the majority of existing music robots are deaf. In other words, they don't know that they are playing sound. Like if I unplug the if I remove one of the drums in the robot here, if I remove the drum, the stick will continue hitting the drum and thinking it's playing. It has no way of knowing that the drum is not there. And obviously, if you have a human musician and you remove the drums, they would say, what the hell are you doing there? They can hear what they're playing. So the ability to listen to the acoustic output has concrete practical applications. So we have done work on understanding what sound you're playing and how loud you're playing and calibrating all that. So that's sort of using audio classification and feature extraction, not as an end task of itself, but as a way to understand what the robot is doing. So I'm going to skip that. And this is the latest iteration. I've done quite a bit of work with robotics. This is probably the most advanced mechanical drumming system. It has full motion control, so it can control the sticks with all the detail and velocity and acceleration that the human drummer plays. It's based on voice coils. So here's I'll just play an example. So you can hear that this is very realistic. I mean, if you can, it might not be that easy through bad speakers and stuff, but it's able to play just as softly, just as loudly, just as fast, move directions. It's a quite expensive piece of equipment, but it's fantastic. And the other thing is it also coupled with a capture system. So we are able to take an existing drummer and capture exactly how they play the sticks, not just when the sticks are on the drums, but also when they're in the air with the camera, and then use that information to drive that robot. So this is the gesture system. We have a camera, and we can capture this performance information in very detail. By doing that, what we can is introduce performer-specific models. So when a human plays the drums, they're not perfect. And I will play you an example. So this is an example, the original recording. This is a human playing it. So it's a human playing a drum roll, just kind of standard drum roll. So listen to it one more time. Oh, sorry. And now this is a mechanical reproduction of the same drum roll. So just doing it kind of as it's written in the music. Oops, this keeps advancing the page. There we go. So you hear it sounds kind of like a machine gun. It doesn't sound like a human playing a drum. And that's because everything is perfect. So we need to introduce these small imperfections that actually is what makes it human. So this is the imperfections introduced. So as you can hear, it's much closer to the original recording, sounds more real. And that brings me to the topic of expressivity, which is exactly these small, tiny details. So in the area of drumming, a lot of electronic drums, if you like go at a store and buy a set of electronic drums, they're just a set of buttons. Like you hit the drum and it plays a sound, but it doesn't play loud, or maybe it plays it louder or softer, but it doesn't change the sound the way a real drum does. So Adam Tyndale, who was a classically trained percussionist, worked on a hybrid model where we use the physical membrane to excite a digital synthesis model. So you get both expressivity and kind of digital flexibility. And the video makes it all clear, so I'll just play the video. So you can use it with different sticks. So it's so that's again like this idea of expressivity is really important. Another example, if any of you are artists and like to draw, you know, compare doing watercolors or using your pencil to draw to using your trackpad. There is this detail that's missing, and there's no reason it's missing. It's just limitations of our technologies and really trying to push for more meaningful interaction. Here's another example. This is an instrument called the soundplane that a former student of mine, Randy Jones, that was his design, and now he has built it, and he's actually selling it. So here he's playing this instrument, and I just want you to notice how expressive, how much detail he can convey with his playing. So you get the idea, but it's really like, that's the type of communication expressivity that I would like to have with computer systems. Another interesting example is the theremin. So the theremin is an electronic instrument. I don't know how many of you are familiar with it. You probably have heard it in science fiction movies. Learning to play notes can be challenging because you are playing in the air. You're not touching anything. There are no strings. There are no buttons. It's just, so I'll show you an example. Here is Carolina Eck, who's an amazing player. So you can see that she's not touching anything. It's just moving her hands in the air. Oops, sorry. And I'll just show you more of a piece just so that you can see how beautiful it can be. Move it a little bit. Okay, so you get the idea. I mean, you can look at this theremin up later. What we wanted to do was to teach people how to play this instrument, and it's really hard. And we wanted to explore virtual reality for that. So what we had is a setup where we had a theremin, a real physical theremin, but we also had a virtual reality system where you were wearing a head-mounted display and you could play as well as a laptop, like a regular desktop screen. And we provided some visual feedback for learning how to play it. So I'm not going to go into the details. Here's the view you would have in the virtual reality, some measurement depending on your training, and some of the performance between the no visualization, the display, and the virtual reality. So we compare those. So that's kind of another example of trying to make this more communication, more interaction with these complicated computer systems. So to conclude, having a body such as sensors and actuators introduces layers of possible failure, but these layers of possible failure provide opportunity for the sublime to occur. Collaboration and communication between different entities, whether they're physical or virtual, has to be deeply personal and communal at the same time. Music is not just pitches in time, but has much richer and nuanced layers of information. So the challenges of, I hope I have convinced you that these are challenges and opportunities, and perception, communication, embodiment, and expressivity also, I think, have applications to general AI systems. Finally, a little bit of self-promotion. If you find any of these things interesting, I just finished 3 courses. They're part of Cadenzi, which is an online learning provider, on music information retrieval. This is the URL. Feel free to email me if you need more information. The first course is free. The other 2 courses, you have to be a member of Cadenzi, but it's pretty reasonable. And if you want to learn more about these topics, this is a good resource. So I would like to finish here, and I would like to dedicate this keynote speech to David Wessel, who was a composer, researcher, performer, and I consider him one of my mentors. I loved his work and his philosophy. It seems like yesterday, but it's been 6 years since he passed away. And lots of these ideas about control and expressivity were heavily influenced by his writings. So thank you very much. I will switch to the regular view, and hopefully we can have some discussion.
Great. George, thank you very much for the great talk. And, Zoom is not yet as great as a face-to-face kind of scenario. So, but on behalf of the more than 100 participants, I would like to give you an applause, okay? So, George, frankly, I treat you as my mentor. And I very much resonated on your comments about this multidisciplinary research idea. And I thank you actually not only to introduce me to the amazing ISMER research community, but also sending your brightest student and Graham Pursuit from Canada to Singapore. And we have done some amazing research that you know that as well.
Yep.
Yeah. And also, and we both seem to attract some amazing musicians to our class. Yep. I'm probably the only sound and music computing class in Singapore. Typically, we always have a concert toward the semester end. But unfortunately, because of this COVID, I'm not sure whether we are going to do that this year. But at least in the past, we have always done so. And even including this computer science research week. Last year, we had also organized a concert. Frankly, when you come here next time, I expect you to bring your saxophone from Canada to Singapore.
Yeah, it's right here.
Oh, that's great.
You can't see it.
All right.
Here, there you go, one of them. I have lots.
Okay.
This is actually a recent acquisition. This is a vintage saxophone, so it's about 100 years old.
Very nice. So, another thing is that one of my students, and Aaron Shinoi, he was actually the first Grammy-nominated music producer in Singapore.
Oh, fantastic.
Yes, I'm so happy to kind of promote this idea of multidisciplinary research and multi-talents, because our students are not just we don't educate them just to program, to learn certain things here, but as a whole, people have a lot of talents, right? So that's why we give them the opportunity to learn amazing and interesting stuff, okay?
Yeah, I would say, it's important to do both. Like you have to be to some degree interdisciplinary yourself, and you can't put yourself in a silo. but at the same time, there's so much knowledge that there's no way you can learn everything, and you have to collaborate with people. And the only way, like, again, it's all about communication, and you need to be able to speak their language. So, if you are working in, I don't know, machine learning, and you want to do something with robotics, you don't need to be an expert in robotics, but you need to know enough to be able to talk to someone in robotics and talk to them in a way that they can map what you are saying to what they know. And it's that level of, it's almost like, kind of like being able to speak a foreign language good enough to order food at a restaurant, not to have a philosophical conversation or to write poetry, but be able to do your everyday life. So if your graduate students, strive to be really fluent and experts in one area, but also try to be good enough to be able to talk to people in other areas.
I cannot agree more with you, man. And frankly, I do also do this interdisciplinary research, and I collaborate with clinicians. We generate music actually for patients' rehabilitation. Can you believe that?
Oh yeah, that's very cool. Yeah. I'm seeing a question at the chat.
All right.
I'm curious how human perceives depths and directions of instruments. I think this is very important for expression. Can machine do these simulations? I assume you mean the locations in space, like if you are in a concert hall, where each instrument is in the space and how the reflections work and that stuff? Is that what you're asking? Yeah, okay. So yes, people have worked on that. There are systems that can, well, there's two things. One is having the computer listen to, let's say, some recording and tell where each thing is. So that's more the analysis side. And there's also if I give you samples of one instrument and another instrument, I want you to create how it would sound in a concert hall when you place this instrument here and this instrument there. There are systems that do this very accurately that are not real time, and they're used to design like concert halls. So there is area like architectural acoustics, but they're not real time. And there is some work that's done in games and game engines that tries to do sound propagation, not perfectly, but reasonably, like things like if there's a wall, the sound doesn't go through, and those try to do it in real time. And yeah, you're right, that is important, and I think that it's an important problem. And actually, one of my former PhD students is currently in Japan, but it's coming back to Canada, and he's going to be working with a collaborator of mine. We were kind of co-supervisors of him in his PhD, but now my colleague is at UBC, and this student is going to go to UBC, and he's going to be working on 3D audio scene reconstruction from audio. So like having the recording and then figuring out where everything is in space. Any other questions?
To the audience, and please type your questions in the chat box.
And if somebody wants to just talk, that's also fine. I think we will be okay as long as too many people don't get the microphone. You can also raise your hand in the participant window. But
I use this technology to the full.
Yeah. Feel free to just ask. I'm okay with that.
Yeah. So meanwhile, I just wanted to let you know, I'm also very interested in this talking about the language, right? And if we don't speak the same language, and we can't even communicate. Yeah. So therefore, and we build a system, a karaoke system, to help kids to learn a language.
Oh yeah.
Yeah. Oh, we have a question here.
Yeah, what do you think music analysis should be? Data-driven based or rule-driven based, which may lead to AI music generation, I think. Well, I guess, that was part of my point in the Markov logic networks is that, and I'm not saying necessarily that that's the right way, but it has to be both. You can't just have one or the other. You can build, people have built systems that are both using a data-driven approach and a rule-driven approach for AI music generation. But I think that they're rather limited, and they also are very, the typical music generation system works as follows. It gets a corpus of data, analyzes it, and then produces music that sounds like the data that it analyzed. And that's not how a musician plays. And we can, like a musician is able to do stuff without access to large corpus of data, or play in styles that they're not familiar with. They're not going to play great, but they're still able to play. They're able to correct mistakes. They're able to understand rules. And so there's a lot of work in AI music generation too. And it's not, in my opinion, most of the interesting work is not just simply using a more complicated deep learning network architecture. It's more complicated than that. But thank you, that's a great question. Any other questions?
Yes, I also agree with your comments about deep learning. Nowadays, actually, a lot of students are very interested in deep learning. But I would like to say the normal machine learning techniques are still useful. I have a question to you, George, and before we see another question, okay?
Yeah.
For the my class in sound and music computing,
yep.
Previously, I only focused on the music aspects, but from this year on, because of this general AI and specialization, I broadened this spectrum a little bit to cover things not only about, for example, automatic music transcription, but also automatic speech recognition and sound even detection. Because in my view, even this technology and then the system architectures are very similar. You can see we are doing this conversation here, but when you started to play music, for example, if we still have an automatic speech recognition algorithm going on, it simply does not make sense of the music signal if it's a speech recognizer.
Yeah.
So then, of course, and then everything that we perceive could be a piece of speech, a piece of music, or some environment sound like bell ringing and something like this. So this is actually towards a more general kind of artificial intelligence. What do you think?
Yeah, I mean, that's a very interesting point. I'm not sure I can answer it in any meaningful way in a short time, but yeah, like there's the, for some, like you're right, in some concepts, like for example, hidden Markov models are used in speech recognition and are also have been used for chord detection. And in some ways you can kind of make a parallel that the phonemes are the sounds and the phonemes are the chords and the sound is the sound in both. And then they, in both in speech and chord recognition, they have moved from hidden Markov models to deep learning approaches these days. But the more deeper question of if you had a system trained one way, can it be used for another task, and can it transfer? Those are hard questions. And clearly humans are able to reuse that stuff. Like if you have, all the learning you did to understand your own language, if you learn a second language, you don't start from scratch. You're using a lot of the same machinery. And yeah, so I definitely think exposing the students more to AI techniques is a great idea. And it's just also happening naturally. Like it used to be that a lot of students would finish a computer science degree and not ever have heard of a classification as a problem or a support vector machine. And these days, the curriculum, I assume NUS is similar to everywhere else, that there's much more data mining, machine learning courses, and students are much more familiar with that stuff.
Yes, we have another question now.
Okay, here, yes. In a lot of the examples, you have mentioned the importance of physical aspects of music. For example, the way that a violinist relies on feedback, the way that a drum roll relies on stochastic imperfections. What about music styles that are already digital? Are they more amenable to AI music generation? Yes, for sure. If you want to generate kind of slow EDM, there's systems that, at least to my ear, they don't sound any different than humans. I don't know of any AI generation system that sounds good enough for jazz. And I'm not saying that those digital music styles are not good or bad. It's just that they're different. And personally, as you know, from my own interest, I'm much more interested in, and that's why as a musician, I do have an interest in keyboards and samplers and all that stuff, but most of the time I enjoy much more playing my saxophone than I enjoy playing a synthesizer. So,
Very nice. All right, to the audience, and you have a chance to ask the last questions. All right.
Okay, so thank you so much.
Thank you very much. Oh, we have another question.
Oh, yeah, okay. So thank you for the talk. Not a question, but a more of a compliment. I believe such technology has the great potential to prevent instrument-specific injuries. For example, the fingers of the pianist or those of the bass guitar player. Really nice work. Yeah, in fact, I did have some work on piano playing, and it's on kind of music pedagogy, an area that I know Professor Wang also has done a lot of interesting work. And most of the systems that, for example, help students learn piano, the main idea is that they show you a piece, you play it, and then the system analyzes what you play, and the system says you played this note wrong or this note wrong. But the system doesn't know how you are playing it. And if you have learned piano, you know that how you hold your fingers can be very important, and you can really mess up your carpal tunnel and stuff if you're not doing the right thing. So what we did is we build a system, you know, in piano playing, you're supposed to kind of hold your hand relaxed and not play like this and not play like this, kind of a natural position. So we had a system with a camera that was detecting hand posture and trying, we didn't go into injuries, but just simply like giving some feedback to students when they're playing about this. So it's a very, very good point, and I think there could be much more work in that area, for sure. Thank you.